Walaikum assalam. So I'm going to share my screen. Can you see my screen?
Yes, sir.
Okay. Uh, so now we are in chapter 2, transient analysis of three-phase power system. So, uh, I mean, I will basically go through the book and try to explain it a little bit more. So in normal operating condition, a three-phase power system can be treated as a single-phase system when the loads, voltage, and currents are balanced. So probably you have studied it. So these things are basically recapping the things that you have done in your power system course in undergrad. So in a balanced um, electrical system, by balanced we mean that all the three phases have the same amount of load, voltages, and currents. In a power system, we know that it's a three-phase system. So you have basically three lines. So we call a system that is a balanced system if the current, that means if the load connected to, let's say, phase A, phase B, and phase C is having the same load. That means the current that is flowing through phase C is IC, current flowing through phase A is IA. So IA, IB, and IC are the same. As a result, the voltages in the three phases are also same because of the same impedance of the line. If either of these is not equal or is not same, that means if, for instance, you have a load connected to phase A, which is much higher than phase B or phase C, for instance, then IA is not equals to IB and IC. And such a system is not balanced anymore. So in a balanced system, if all the currents and the voltages and the impedances, if they are the same, then we can actually analyze the system using a single phase analysis. So we know that these phases are basically, if they are balanced, they're having the same amplitude, but they are only the difference is the angle. So they are 120-degree apart from one another. So if you have, for instance, if this is IA, this is IB, this is IC. So if you know, for instance, the value of IA, if they are all balanced, that means they are of same magnitude. So you can only use a single phase and you do not need to analyze for the three-phase system. You can simplify the problems. Am I clear to you?
Yes, sir.
So you already know it, right? Taina, is this things new to you?
Yes, sir.
Okay,
And just proceed, sir.
okay. So then I will go a bit slow if the things are new, or otherwise I will go a bit fast. So in a balanced system, this is ideally in normal conditions, this is almost never the case, because you can assume that one of the phases is connected probably to a large building or to a large loads. Probably the other phases are connected to a small loads. As a result, the current flowing through the line will not be same. This is what you normally expect. Okay, but I mean, if you do not, if you, if you neglect the small differences, then the overall currents is more or less similar. I mean, they are of course not exactly equal, but they're very close to each other. So if you go to IUT, for instance, you can If you stand in the first floor in the first academic building in the level one, you will see that um, there is a box just near the stairs, and from there you can see that they have the three-phase voltage readings. So you will see that the three-phase voltages are more or less very close to each other. They are not exactly the same, although, but they're very close to each other. Okay, so that means that if they are balanced, we can only analyze a single phase. We can do the we can solve the problems very easily. But if they are unbalanced, for instance, the unbalance is very prominent, for instance, in the case of a fault. So if fault happens in a power network, so power networks are, as I mentioned, we have generators. We have generators, and then this generator voltage is stepped up using a transformer, because the generators are normally have an output voltage in the range of maybe 10 kilovolt to up to 20 to 25 kilovolt. They are almost never exceeds 25 kilovolt. The reason is that uh, inside the generator you have windings, and these windings needs isolation. That means it needs to be insulated from one another. Otherwise, if you do not insulate the windings will get short circuited. So if I, for instance, show you a generator, uh, so this is the uh, generator windings. So you can see that the winding is laminated, and it is also insulated with probably paper insulation. Okay, so all these figures you can see, if the generator is rated for a small power, then probably there is only enamel coated. If it is rated for a high voltage and high power application, that is probably insulated with more rigorous insulating materials. For instance, here you can see that is probably insulated with paper. On the other hand, this one is only enamel coated, so it's coated with a paint for the insulation purpose. So I was talking about why the generator output voltage almost never exceeds 25 kilovolt. In most of the cases, it's only limited to maybe 11 or 16 kilovolt. The reason is that if you increase the voltage, you also need a lot of insulation here. So all the spaces here will take the insulations, and the conductor size will be reduced significantly. As a result, the current carrying from the generator, current output will be low. So to solve these problems, normally we do not exceed the output voltage of the generator. We normally do not design the generator uh, to go beyond maybe 20 kilo, 25 kilovolt. But the transmission network has a much higher voltage levels, which is in the range of can be 132 kilovolt, for instance, in Bangladesh, or it can be uh, 230 kilovolt, or it can be 400 kilovolt in our country. So these are the different voltage levels. So you can see that the voltage is much higher than the generator terminal voltage. So as a result, you need a transformer to step up the voltage to the transmission level. And then you transfer this using the long transmission line that you basically see. And this generator and transformer are located in the generating station. For instance, in Bangladesh, Ghorashal can be a case, or Ashuganj. So you have the generators, the transformers connected to the power station. And then you have distribution substation. So basically, you step down the voltage from this high voltage level using a transformers, of course. And so you step down the voltage, and then after stepping down, the voltage comes to 66 kilovolt or 33 kilovolt. And then it further is stepped down to, it can also go to 11 kilovolt. Okay, so in the distribution line, when it comes to your home, it becomes 400 volt line to line. Okay, and in this power networks, there may happen that it may encounter fault, or fault is an event that is of course not wanted. So what is a fault? Fault can be, so we have this three phase lines. So it may happen that one of the line, uh, maybe because of the storm or maybe because of the weather, it gets uh, disconnected, so it may be broken, and then it touched the earth. So in that case, uh, maybe this line has broken and then touched the earth, so it is a fault. So it's not, the current is not going to the load, it's instead going to the earth, so we call it a ground fault. And it may happen that you have only one of the conductor touches the ground and the rest two are in healthy condition. So this kind of fault is called a single line to earth fault. You may also have a line to line fault. So one of the line may touch the other. That means it may be broken, or some, I mean, because of the mechanical damage, it can touch. Because of the high wind, it can touch the other faces, and there will be short circuit between the two faces. It may happen that two of the faces are short circuited and then it may touch the ground, so we also call it line to ground fault. Or it may happen that three of the phases got short circuited, that means they got connected. For instance, it may happen that uh, uh, because of the tree, uh, because of the tree branches falling on the line, three of the lines may become short circuited. Or it may become three phase short circuited and it may touch the ground. So we have all different combinations of short circuits. So these short circuits, whichever short circuit or whichever fault it will create a very high amount of current to flow through the system. Because previously, the three phases, I am drawing these three phases, are connected to loads. So your house was connected, and your house has uh, different loads, which can be, the current that is coming to the load is not extremely high. That is, the system is designed to handle this current. But if you have a short circuit, that means you are basically bypassing the load and then it's connected to ground. So if a short circuit happens, that means that at that moment a very high amount of current will flow through the system. Am I clear?
Yes, sir.
So a very high amount of current will এগুলা কি আমি জানা কথা বারবার রিপিট করতেছি? আমাকে একটু বুঝতে হেল্প করো। You know all these things? Can someone help me? Are you familiar with all these stuffs? Acha, okay. Okay. So we have these all these different kinds of faults, and all these faults will have very high amount of current to flow through the line. For instance, if phase C is shorted, then there will be very high amount of current flowing through phase C. If I mean A, B, C, all these three phases are shorted, there will be an extremely high amount of current will flow through all these three phases. Okay, and to protect this high amount of current, normally we have a equipment called circuit breaker in the line. So the job of the circuit breaker is to isolate the unhealthy part, or let's say it's like uh, for the case of a human, if someone gets cancer, for instance, then you try to cut that part away from the healthy part of the body to save the rest of the body. So the same is true for the power system. So if you have a fault, for instance here, so your job is basically to cut off this part of the system, okay, from the rest of the system. So this cutting down part is basically taken care of by the circuit breaker. So the name suggests it's a circuit breaker. So it will basically break the circuit. So it will open the circuit. And this circuit breaker is normally takes the command from a relay. So in the power system, you have measuring equipments like uh, a voltage transformer or a current transformer. So you also have, let's say, a voltage transformer. So a voltage transformer will basically uh, tell you what is the system voltage, what's the line voltage, and a current transformer that will basically measure how much the current is flowing through the line. So this current transformer will notice if there is a short circuit. The current transformer will notice that there is a high amount of current flowing through the line, and it will give this signal to a equipment called relay. So relay will basically take the decision that, well, there is a very high amount of current flowing through the system, so this must be a fault, and the relay gives the command to the circuit breaker. We call it a trip command. So the circuit breaker will instantly trip. That means it will open the circuit from the healthy part. And that's when comes the transient part, because when the circuit breaker opens, then because of the energy storing element into this network from here and then from here, once you have the open part, previously the circuit breaker contact was closed, and now once you give the open command, it becomes open, and then the two sides of this breaker, one on the left side and the other on the right side, they will oscillate with different voltages because of the energy storing element into the grid. By energy storing element, I mean the capacitors, the inductors, and the capacitors and the inductors. These are mostly the stray capacitors and stray inductors. You cannot see it in your open eyes, but they always exist in the power networks. So when the circuit breaker opens, as the voltages are oscillating between these parts, so you will have a transient voltage until the oscillating part basically damps out. So in the first class we have seen it. So if we have a RLC circuit, so the RLC circuit will basically damp out this oscillation. It's like this, it will damp out eventually. But during this damping out process, there will be a transient voltage appearing across the breakers. Okay, and when you have a short circuit, at that time, before the short circuit, you are having a load current which was more or less fixed. So, and suddenly, for during the short circuit, you will suddenly have a very high increase in current. Normally, it is 10 times higher or even more higher than the load current. So, for instance, if you have a 1 kiloampere load current, if you have a short circuit, it can go as high as 10 kiloamp or even more than that. So suddenly the system will see a very high amount of current flowing through the line. So in this part of the book, we will basically try to analyze, try to see what happens if we have a unbalanced network. So in case of a balanced network, as I said, that we can only use a single phase and analyze for the single phase, and we will get the value for the rest of the phases, because these phases are separated by 120 degree. I mean, they are, the only difference is that the angle. But if you have a unhealthy condition, I mean, if you have a asymmetric condition, that means if the three phases are not symmetric, if the currents are not symmetric, this can be the case when you have a single line to ground fault, or double line to ground fault, or double line fault. So all these cases are basically a asymmetric fault, and statistically, most of the faults, almost 90% of the faults are of asymmetric nature. That means the symmetric fault is when three of these phases are basically short-circuited. That means that if three of the phases are short-circuited, in all of the three phases, same amount of high short-circuit current will flow. So it is called a symmetric fault if three of the phases are short circuit. So it can be a three-phase fault, it can be a three-phase to ground fault. So both of these two cases are symmetric fault. The rest of the cases are asymmetric fault. And statistically, as I said, most of the faults in a power network are of asymmetric nature. That means that if only phase A is short-circuited, then there will be a high amount of current will flow through phase A. So in the phasor representation, maybe phase A is having a very high amount of current, whereas phase B and phase C is having not so very high amount of current. So this particular case is called uh, asymmetric fault, and it's giving an asymmetric current. And there was a engineer whose name was Fortescue. So he derived the he derived the condition how you can use the asymmetric uh, three-phase faults, and you can convert it to a symmetrical components of three symmetrical components, and how you can use those symmetrical components to analyze the fault. So the idea is very pretty simple. So here, so in case of a balanced network, so all these three phases are same. So this is the balanced case. So here you can see that this is phase A, phase B, phase C. So if you have an unbalance like this, the blue one is, you can see, is of much longer magnitude than the red and the yellow one, as well as the angles are not same. So the Fortescue's theorem tells that if you have a n number of unbalanced phases, that means you can represent this as a sum of n uh, n minus 1 balanced symmetrical components plus one zero sequence components. By the zero sequence means all of these three all of these three phases have the same angle and it doesn't change. Okay, so that is what the comes zero sequence comes in. তোমরা কি sequence zero sequence positive sequence এর সাথে used to? Are you used to with this zero sequence positive sequence negative sequence? সবাই কি used to? আপনারা সবাই কি জিরো সিকোয়েন্স পজিটিভ সিকোয়েন্স নেগেটিভ সিকোয়েন্স ব্যাপারটার সাথে ইউজ টু? Okay, so you can see that if the magnitude changes, I mean if the asymmetrical components changes, you can represent this by the sum of three symmetrical uh, components. This one is symmetrical, is called positive sequence. So here you can see that the blue line, and after that you have the yellow line and then the red line. Here it's blue and then the red. So if this sequence is positive, this sequence is opposite of it. So then you have to consider from this part. So this is a negative sequence. If this is a positive, then if you come clockwise, then it becomes negative. And the zero sequence, it doesn't have any angle. I mean, all these three phases having the superposing on each other. So if for any asymmetrical condition, you can represent this by sum of these positive, negative, and zero sequence components. And of course, the magnitude will change, but the angle between these three phases will be the same. So you can see that it's always 120 degree, it's always 120 degree, and they are of same magnitude. So each of these three are balanced and symmetrical. Okay, so if I change it, you can see that they are always balanced. Okay, you can see. So for sometimes the positive part may become larger and sometimes negative part may become larger. Okay, so you can see that, but they are always balanced for any given asymmetrical condition. Let's say for any given asymmetry, you can see these three, positive, negative, and zero sequence, are in balanced condition. They are having the same magnitude, and only each of the faces in positive and negative sequence are separated by 120 degree, whereas in zero sequence all of these three faces are having the same angle. আমি কি বুঝাতে পারতেছি এখন পর্যন্ত? কারো কোনো কোয়েশ্চেন আছে? Are you there, everybody? সবাই কি আছো এখানে? Okay. So here are the um, equations for the symmetrical components in three-phase system, where VA, as I shown here, VA, this can be the red line, VA can be written as the sum of positive sequence, negative sequence, and zero sequence components, like VA1 plus VA2 and VA0, where VA1 and VA2 are the positive and negative sequence, and VA0 is the zero sequence component here. So similarly, VB can be written as the sum of VB1 plus VB2 plus VB0, and VC can be written as the positive, negative, and zero sequence for the C phases. আমি কি ক্লিয়ার এখন পর্যন্ত? একটু রেসপন্ড করলে ভালো হয়। Am I audible?
Yes, sir.
Okay. Can you follow it up to now?
Yes, sir. I think we can proceed. We can like just proceed.
Okay.
Yes, sir.
Okay. So So VA, VB, and VC can be written as there is a matrix which is called A, which is basically is written like this, where small a represents a multiplying factor of 1 and 120 degrees. So A, if you multiply small a with anything, it will shift 120 degree. Okay, and VA0 is the zero sequence, VA1 is the positive sequence, VA2 is the negative sequence components. And so for phase A, VA is, if you multiply it with the matrix here, so it will be VA0, VA2, VA1 plus VA2. VB will be VA0 plus A square, VA1 plus A VA2, like this. The A operator rotates any phase or quantity by 120 degree, and inverse relation can be written. That means that if you have a asymmetrical condition for different VA, VB, and VC, you can calculate VA0, VA1, and VA2 by, by inversing this. So from here, if you inverse this part, you get 1 over 3, and this part. So you have, so for any given asymmetrical VA, VB, VC, you can calculate the sequence components for phase A. So if you know for the phase A, for any cases, you will also know for the phase B and phase C as well, because these are only shifted by 120 degree. Okay, so am I clear up to now?
Yes, sir.
Okay, and then comes the sequence components for unbalanced network impedances. So you can go through it, chapter 2.2. I will go to chapter 2.3 directly. You can go through chapter 2.2. The sequence network. In the case of an unbalanced load or fault supplied from balanced or equal phase impedance, the unbalanced portion of the physical power system can be isolated for study, the rest of the power system being considered as balanced. In such a case, we determine the symmetrical components of voltage and current at the point of unbalance and transform them to determine the system ABC quantities. That means that if you have a fault, you basically uh, represent the networks by three sequence networks: positive sequence, negative sequence, and zero sequence network, where the positive sequence network is having a voltage source. So the current, that is the positive sequence current, when it is flowing through the system impedance Z1, and it is having a voltage source. The negative sequence current does not have any source voltage, so it has only the uh, impedance Z2, whereas the zero sequence current, that means in case of a zero sequence, you see that the current does not have any, all the three phases have the same angle, so it does not change. So basically all these currents will go through the neutral. So have it will go through this Z naught impedance. That means it will not go through, it will not flow through the line, it will flow through the neutral part and through the ground if it is if it is a ground. So basically you represent the positive, negative, and zero sequence uh, networks when you have a fault. Okay, so and you can represent this VA0, VA1, and VA2 uh, by this matrix, where the one is for the positive sequence part. So for the positive sequence part, you have only the VF, or from the fault location, the Thevenin voltage that you can see, that is the VF. So you have the VF minus this 0 multiplied by 0 a I1 IA0, which is 0, and Z1 multiplied by positive sequence current. So for the positive sequence voltage VA0, you get VA0 is equals to Thevenin voltage minus positive sequence impedance multiplied by positive sequence current. And uh, VA0 is basically there is no voltage here. For the zero sequence, there is no voltage, so only the impedance multiplied by IA0. For the negative sequence as well, there is no voltage. Okay, so I'm not going to extend anymore for today, but it is your task to follow until chapter 2.3, and then if you have any question, we can always discuss at any time.
Okay, sir.
ওকে স্যার। স্যার
Do you have
ফ্রাইডে তে কি ক্লাস হবে
no,
ফিজিক্যাল?
this Friday there will not be class because I have taken leave on this Friday, so I'll not be available. But I would recommend to have a class on Sunday if possible.